ค่ะเดี๋ยวอีกสักครู่หนึ่งนะคะทุกท่านค่ะสามารถเข้ามาฟังสำหรับหัวข้อการบรรยายได้ ซึ่งวันนี้ค่ะเราก็จะมีการบรรยายตลอดทั้งวันนะคะซึ่งแน่นอนว่าสำหรับงานนี้ก็จะจัดขึ้นทั้งหมด3วันด้วยกันค่ะแล้วก็จะมีการสัมมนากว่า20หัวข้อกันเลยทีเดียวค่ะขอเสียงปรบมือให้กับมิสเตอร์คาร์ไมเคิลกูริอาตี้แอนด์อัลเบิร์ตซิงจากทางมาร์คเดอะมิสอัลฟาขอเสียงปรบมือด้วยค่ะ
Okay, good afternoon, everyone. I have Albert Sang with me, and my name is Carmichael Gugliotti. We're here to present on interaction study between direct metallization technology and acid copper technology. Closer. Slides. Okay. All right. So we will first talk about direct metallization development and the research that McDermott Alpha has done over the last 30 years. And then we'll get into a discussion on electroless copper versus direct metallization. We'll talk a little bit about sustainability initiatives tied to direct metal. Then we'll talk about electrolytic copper, direct plate, DC current versus pulse plating, the cost benefits of pulse plating, and then we'll compare everything and put a maximizing performance study together, and then we'll have some time for Q&A at the end. So the first part we'll talk about is direct metallization and the development history. So what is primary metallization? So primary metallization focuses on getting holes and microvias to be conductive, right? So it's required for all PCBs and substrate types, and it's used to connect all the various layers together, and it's required for every process that needs electrolytic plating to occur. So we have some examples here of a microvia. We have examples here of a through hole as well. We're going to primarily focus on through hole reliability for this presentation. So reliability is critical when it comes to PCBs, and what the definition of a reliability for our case here is talking about what is required for a bare PCB board to meet all of the minimum requirements of assembly, run through the process, and then last through its product life, shelf life, and performance in the conditions, whether it's automotive in a vehicle or mobile phones in a pocket or exposed to the temperature, rain, those kind of things. So all of our PCBs start with a non-conductive base material called laminate. We then do drilling and desmear to create our shapes, and then we use our either carbon or graphite technology to make these points conductive. We etch away at all of our copper locations to get a clean copper surface, and then we go into our electroplating copper process to fill or conformal plate all of our features. So we'll talk a little bit about the history of metallization and over the long term. So back in the early 1960s, we came up with the first mass production of colloidal palladium electroless copper processing, and that started to be used in high-layer multi-count PCBs. About 20 years later, in the 80s, the first direct metallization process came out, which was carbon-based. And then in the early 90s, the first graphite process came out, so comparing carbon versus graphite. As technologies expanded in the mid to late 90s and then early 2000s, we made improvements in the technology and the equipment designs so we could optimize the process for higher end technology. And the 2017 and going up to about last year, we've started to see the MSAP processing, improvement in high HDI designs, and as this technology has come up, we've had to make newer processes to compare. So Graphite Gen 2 came out in 2023, and it combines both the graphite system with a new wet edge technology, which helps further improve our capability and make it an optimal choice for MSAP and HDI designs. So before we got into our experiment to show the reliability and compare the most efficient process, we wanted to compare just across our direct metallization products. So we looked at 4 different tests to determine which one of our DM processes that exist are going to be the most efficient and useful for this process. So the tests are propagation test, backlight, initiation time, and time for complete coverage. The test uses 2 different systems. So we did a high-speed camera propagation video, which uses a single pass process to look at initiation time and complete coverage time. And then for our propagation rate and backlight tests, we did a double pass process. And I have here the beaker study samples of each of the process steps that are used in the process flow listed above. So each of the tests were then mapped out over an average of multiple readings. So you can see in our first one here, we have our propagation rate. Because coupon design and lot-to-lot variation, we don't want to use a standard number, so we use what we call RCR, or relative coverage rate. So you take one condition as your baseline, which we use as our carbon-only process, and give that a rating of 1. So then we look at the comparison across our other processes, a carbon-graphite mixture, Graphite Gen 1, and Graphite Gen 2, to see if we're improving the coverage rate across these pieces. And you can see that from left to right here, carbon is the lowest performing, and Graphite Gen 2 is the highest performing from a propagation rate. And the Gen 2 graphite shows about a 5.5 times increase over the carbon-based system. On the right here, we have our backlight test. The goal of this is to have the highest rating possible, scores on a 1 to 10. The higher the rating, the better the coverage. And you can see all of our processes pass above our 8 here, or 8.5 millimeters minimum spec, and the carbon graphite mixture actually performed the best. Then using a high-speed camera, we cut a test board in half, and then we actually started the plating, and we were able to record the plating over time, so we could see when the performance started, and then when the copper plating fully covers the inside of a whole wall. These trends follow the same from the initiation and coverage. You can see that it takes the carbon one the longest amount of time to start and complete the coverage, with the full plating time taking about almost 4 minutes. And then you go down, you have carbon graphite, Graphite Gen 1, and then Graphite Gen 2 is the fastest, with initiating in about 5 seconds and fully plating the whole wall in about 40 seconds, showing a 6 times increase in efficiency from our black hole process, or from our carbon-based process. We then took some screenshots of the videos so we could show clearly where we're at. You can see the initiation start, you can see it building up towards the middle, and then you can see our point of full coverage. We have these marked with a green box and a red arrow. So you have the Graphite Gen 2 here, then Graphite Gen 1, and then moving down here, you can see our carbon and graphite mixture and our carbon-only process. So when we compare these 4 tests, we're able to see that the performance is best using our Graphite Gen 2. It's faster propagation, had a good backlight, and then was faster to initiate and completely cover. So we then selected the Graphite Gen 2 as our direct metal process that we're going to compare to electroless copper, and then bring it into the reliability tests. So I'll turn it over to Albert to run through the description between electroless copper and direct metallization.
Okay, thank you, Carmichael. Now let me try to explain you the difference between the DM and the electroless copper. First of all, you can see this is the picture of the electroless copper I think most of you people, you know, after the electrolyzed copper, we deposit a thin film of the copper. And the function is to do the pretreatment of the electrolytic copper plating. And for the carbon DM or graphite DM, we deposit carbon or graphite on the laminate to form a conductive film to replace the electrolyzed copper. So this is the main difference between the electrolyzed copper and the carbon DM. And then we can see through this procedural comparison, the procedure before the electrolyzed copper and before the carbon DM are the same. You go through elimination, drilling, dismear, and for electrolyzed copper, you need to deposit the palladium. Palladium is the catalyst to do the pretreatment of the electrolyzed copper deposition. And for the carbon DM, we are simply to deposit the carbon or graphite. And then we do copper cleaning to remove the excess carbon or graphite on the copper surface. So basically, the carbon DM procedure just similar the palladium procedure of the electrolyzed copper, but we don't need the chemical electrolysis reactions in this bath. So, and to compare the difference between the carbon DM and the electrolyzed copper, we highlight the advantage of the carbon DM at this point. Because of the procedure is shorter, so we have less water usage, and we have lower power consumption. And because of significantly less chemical used, so the waste generation is much less comparing with the electrolyzed copper. And because of fewer steps, so fewer chemicals, I have another slide later, fewer chemicals used in carbon DM. And no pressure metals. Pressure metals means palladium. You know the main cost of the electrolyzed copper comes from the palladium. So for carbon DM, you don't need the pressure metals. And no formaldehyde, no dangerous chemicals, which meet the EHS requirement. More safety for your apparatus, more safety for your factory. Okay, and it reduces the total footprint of your equipment. The total length can be reduced about 50%. Okay, and it's also decreased the uncertainty of the supply chain. Okay, and I would like to share you some technical data on this. I think most of the people knows that the bonding strength on the interconnect is more and more important for the electronics. Right one is the photo comes from the electrolyzed copper. So far, it still have higher chance to get this kind of defect. Narrow void found between the interface of the interconnect. But through the latest version of the graphite generation 2, you can get the perfect bonding strength. You can get the perfect clean interface on the interconnect area. Okay. And about the maintenance of the process, I think most of people knows for the electrolyzed copper process, the alkaline concentration and the formaldehyde concentration is very difficult to control, especially while the economic is down, your utilization is lower, and then the variation of the concentration becomes very big. So it's a kind of difficulty for the operator, for the supervisor to keep a stable chemical reaction in the electrolytic copper base. And it has many components in the electrolytic copper base. So during the low utilization situation, it will become more difficult. And that means your running cost will get higher and higher. But for carbon direct metallization, because the main consumption only comes from drag out, so the chemical stability is very high. So that would be very easy for your operator to control the line. And that is a very short-term learning curve for your operation division. And now, here is the procedure comparison of electrolytic copper and the graphite generation 2. And we calculate the chemical replenishment and calculate the waste chemical treatment. You can see the difference, huge difference between graphite generation 2 and the electrolytic copper. And for me, the most important thing is there is no dangerous chemical used in in this process in the graphite generation 2. No formaldehyde, no dangerous chemical additives. So it will be more safer for your operator, for your factory. And Carmichael talked about there are several generations of the carbon direct metallization, from carbon to carbon and graphite mixture, and to graphite generation 1, and now it's graphite generation 2. What are the differences between this process? We call it dry etching and wet etching. This is the procedure of the traditional carbon and graphite procedure. We have conditioner, rinse, carbon, and graphite deposition, and we have fixed all blow-off procedure to adjust the coating thickness. And then we have a dryer, and then we have final micro etch. But for the latest version, we call it wet etching procedure, because after conditioner, and after the graphite coating, we have etching directly. We don't need the dryer anymore. So comparing the traditional dry etching procedure and the latest wet etching procedure, we eliminate 2 dryer and 2 blow-off. This can save the power consumption more, okay? And because of better formulation with a better wetting capability, this new process can manufacture very high-end product. According to our test data, we can manufacture the via size small down to 25 micrometer. Yeah. And also, we have a better wetting capability on the latest version of the graphite solution. Okay, so this is total 3 dryer, and this one only 1 dryer. So it has saved a lot of power consumption. Okay, and let me try to explain a little more about dry etching and wet etching. In a traditional shadow, while the graphite particle coating deposit on copper surface, this origin color is copper, and the graphite after coating has a dryer, so the water between the graphite particles are all removed by the dryer. But for the wetting process, it still has some solution between the particles. So while go to the etching step, the solution can attack the copper directly, just like this way. So it can result in a lower etching amount. And the lower etching amount is the basic requirement for the high-end PCB manufacturer. Okay, and comparing with the electrolytic copper, the graphite generation 2 is a more sustainability process because of lower power consumption, fewer waste treatment, and less water usage. And it also has a smaller carbon dioxide footprint. Okay, so now I turn back to Carmichael.
Thank you, Albert. So we're going to switch focus for a little bit here then, and we're going to move away from the primary metallization steps with the direct metal or electrolytic copper, and we're going to move to electroplating. So we're going to talk about the difference between DC, or direct current plating, and pulse plating. So for DC copper plating, it's a standard process. It's been run for a very long period of time. It's conventional systems with a basic rectifier, standard conventional DC chemistries, and base equipment that's been around for a very long time. It's used to conformally plate both through holes, microvias, and the surface of a PCB board. It's fairly limited on our aspect ratio, which would be less than 15:1. And aspect ratio is the board thickness divided by hole diameter here. Generally, our target when we talk about being capable is to have a minimum of 80% throwing power. Throwing power would be the average copper basically over the surface versus the middle of the board in this picture demonstrated here. The big advantages to DC copper is it's economical to run, it can handle most low to mid technology board designs, and it meets all of the base control for T&Es, IPC specs, Class 3A, and copper structure. But it's fairly limited when it comes to its overall performance, and generally it's pretty easy to drop into existing equipment. You can see it very commonly in the field. So when we move to PPR, or periodic pulse reverse plating, we get into a little bit more difficult work. It's higher technology, higher cost boards. Board thicknesses can go up to 9-10 millimeter thick, and you use what we call a pulse wave. So our pulse waves there's a bunch of different kinds. There's a lot of research into what types of waveforms work better depending on board design and features, but it's a forward current for a longer period of time, and then a drop to a quick reverse for a period of time where you're actually switching the anode and cathode. You do that reverse for a short time, then you go back to the forward. Every time you do that reverse, you're breaking bonds on the surface of the board, so we're breaking our brightener bonds and slowing down the plating performance on the surface without affecting the holes or the microvias, any features on the board. So then when you go back to the forward current and continue plating, you have a higher potential to plate inside your features than outside of them. That reaction is what gives us our extremely high throwing power and the faster deposition rate. The big disadvantages to PPR is that the equipment is expensive, the chemistry is more expensive, and cycles can affect how the performance is. So you can affect your 3A performance, your tensile strength, your elongation, but with the correct waveforms, you can get the advantages without limiting the performance and reliability. I have an example here. You can see over the same plating time, PPR has a nice even distribution throughout the whole through hole, and it's much thicker than our example of DC here, which has thinner copper, and you can see it starts to taper off a little bit towards the center where it's much thinner. So to compare the two processes, we really wanted to look at a cost-price advantage here. So we did some assumptions here and then did some calculations to determine the difference in costs of just purely on copper anodes. So if you look at DC copper and you assume an average throwing power of about 70% from the example on the page before, and you do pulse at 100%, you're going to see, we have some calculations for panels and plating days of the year. You're going to see a difference here of, if we're targeting 1 mil or a standard amount of copper, 25.4 microns inside the hole, you're going to see that you would need to plate 36 microns in the DC process versus the 25 in the pulse process. So that's an additional of about 11 microns of plating copper. which is going to come out to about 15,000 pounds of additional copper you're going to use up in your plating process in a year, which, based on these calculations and this price, is about $45,000 of additional expense in just anodes. So that right there helps cut the cost of the higher rectification cost and chemistry costs for Pulse. Additionally, you're going to buy yourself an increased throughput because every panel that needs to go through this line, instead of needing your 36 microns, which comes out to almost an hour, 57 minutes of plating, you can plate just the 25.4, which is 40 minutes, and save yourself about 20 minutes of plating time per load, which comes out to about a 43% increase in throughput, which is going to buy you more boards per day processed and increase that performance and efficiency of the process. Additionally, you're going to get the savings of not having to go through additional waste treatment processes for your extra copper and etching processes because you can reduce the amount of etch you need to do on each board that comes out of that panel, that tank. So when we took those two things, we compared then, we have our DC versus Pulse, and then we had our primary metallization of graphite Gen 2 versus the electroless copper. We then took those and wanted to compare the reliability performance to see that we could be as efficient or better on a reliability standpoint and then be able to gain the sustainability, efficiency, and cost advantages to the process. So there's a lot of reliability tests you can do. A standard one that's been out in the field for a long time is IST testing. And we used a standard 22-layer test board that we have a long history of working with, following the IPC spec, doing 3 cycles of a preconditioning to match reflow at 230, followed by 1,000 cycles at 150, with the general target being a 10% increase in resistance being our failure point. So we took 4 test conditions here. We did electroless copper and graphite Gen 2 as our 2 primary metallization, and then we did DC and pulse plating as our 2 secondary. So we can compare the interaction between each of these processes and the primary secondary interaction. For the testing process, we would do a standard processing of a PCB. So you drill, desmear, then you do your primary metallization, whether that's electroless or the graphite Gen 2. Then it goes into pre-clean. Then it goes into the electroplate process, which would be either DC or pulse plating. And then we do tint and etch. We route the coupons out. You bake to get rid of any moisture. And then you run your reliability test based on the IPC guidelines. We did 5 coupons for each type, so we can compare and make sure we had a sizable amount that we could be accurate. And then we continued to run all of the coupons to 3,000 cycles, 3 times the standard IPC spec. We have in the middle here, you can see there's 2 through-hole designs on the IST22 layer, a larger hole that is a 0.9 diameter, and then thinner holes that have a 0.2 diameter. And this is an example of what an IST coupon would look like. You solder your joints from top and bottom and connect to the IST machine to run your reliability test. So over the first 1,000 cycles, we saw no failures in any of the conditions. So we then went to 3 times the IPC spec and went to 3,000 cycles. And you can see on this graph here that all of them stayed below 1%. Here's our 5% threshold mark and 10% threshold mark. So there's really no reliability difference between the DM or electroless copper or between pulse and DC plating. I have the raw numbers here to show. We're continuing a second round of testing. We're processing more boards to run at higher temperature to push these conditions further so we can try and get a difference between these. But from the initial results, you can see that there's no reliability difference between the various processes, which means you can then go back and look at whether you're going to get savings or efficiency benefits in another step. We took the coupons, and to verify the performance was good, we also did cross-section analysis, which you can see from each condition, and then we did SEMs of before and after IST cycling to see the difference in grain structure and reliability at the joints. You can see here the grain structure points. This example here is for the graphite Gen 2 and pulse plating. We did it for all 4 conditions. We didn't see any microvoids. We didn't see any common concerns of reliability or failure points or soon-to-be induced failure points. So we felt the reliability was consistent with the results and showed no degradation in the performance. We have some additional IST photos just showing examples of the graphite Gen 2 with pulse, the graphite Gen 2 with the DC. You can see the difference in grain structure, the electroless copper with pulse, and that should be with DC, to show the comparison of the grain structures between the various conditions before and after IST performance. To add on to that, we did another series of reliability tests to make sure that there was no other common ones. I won't go into as much depth in these, but we did the IST22 layer. We did a 6-layer microvia design to check that the microvia reliability and capture pads were clean and good. We did OM testing. We did a via pull testing to make sure that the weak point in our vias was not at the connection between the direct metal and the acid copper, but at either a joint of the inner layer or on the surface. And then we did a whole wall pull away test to verify that we weren't seeing a lot of recession in the through hole feature itself. All of these tests for all the conditions passed. You can read the passing here. But there was no significant issues found in any of the tests. Again, showing reliability was fairly consistent between our electroless process and DC process, or primary metallization process, and consistent between our DC process and our pulse plating process. So, in summary, when we look at our efficiency of the primary metallization, we saw that our graphite Gen 2 performed better than our graphite Gen 1, which performed better than our carbon and graphite mixture, which performed better than our carbon. You can see a significant process control, lower cost, and higher sustainability using DM over electroless copper. So we believe that that's the way we should be going forward. And then when we look at the efficiency of our plating process, we could see a significant benefit using pulse technology versus DC. So when you combine those, it's clear that the pulse process with graphite Gen 2 is going to be the best performing and best way to go. And from a reliability standpoint, there's no difference. So you might as well go with what's going to give us a better sustainability and cost advantage. And then just have a comparison chart here showing the benefits to the primary metallization process. And you can see, combining everything, the graphite Gen 2 and pulse would be our most cost-efficient, most efficient, and reliable process. And with that, any questions?
มีท่านไหนมีคำถามไหมคะ ค่ะ ถ้าไม่มีแล้วนะคะต้องขอบพระคุณค่ะมิสเตอร์คาร์ไมเคิล โกริอาตี้ และอัลเบิร์ต ซิง มาร์ค เจอร์มิต อัลฟา ขอเสียงปรบมือด้วยค่ะ ขอบพระคุณค่ะ และแน่นอนค่ะสำหรับในหัวข้อต่อไปนะคะเราก็จะมีสำหรับหัวข้อการบรรยายค่ะที่จะเกิดขึ้นนะคะหลังจากนี้ไปจนถึงช่วงเย็นค่ะอีก2 section ด้วยกันค่ะและสำหรับหัวข้อต่อไปนะคะก็จะเป็นหัวข้อ Automotive Chain and Development by ดร. ฮาโยะ นากาฮาระนะคะจากทาง NT Information ค่ะในช่วงนี้นะคะขอเรียนเชิญค่ะดร. ฮาโยะ นากาฮาระ inviteและในช่วงเวลาสำหรับเซกชันต่อไปนะคะจะเป็นช่วงเวลา 15 นาฬิกา 15 นาทีนะคะซึ่งในช่วงนี้ค่ะทุกท่านนะคะสามารถพักผ่อนตามอัธยาศัยได้สักครู่ในเซกชันต่อไปนะคะจะเป็นช่วงเวลาที่ทุกท่านเนี่ยจะได้รับฟังสำหรับหัวข้อการบรรยายค่ะเดี๋ยวในช่วงนี้ทุกท่านสามารถเดินเยี่ยมชมงานของเรากันก่อนได้และเดี๋ยวฉันจะค่ะเดี๋ยวขออภัยนะคะสักครู่นะคะโอเคค่ะเดี๋ยวเราจะให้ทุกท่านนะคะได้ รับฟังสำหรับหัวข้อการสัมมนาอย่างต่อเนื่องนะคะจะได้ไม่เป็นการเสียเวลาในช่วงนี้ค่ะทุกท่านนะคะที่อยู่ในบริเวณงานนะคะเรียนเชิญทุกท่านมายังบริเวณด้านหน้าเวทีค่ะในช่วงสำหรับหัวข้อการบรรยายหัวข้อต่อไปนะคะจะเป็นหัวข้อ Automotive Trend and Development by ดร. ฮาโยะนากาฮาระจากทางบริษัท NT Information นะคะขอเสียงปรบมือให้กับดร. ฮาโยะด้วยค่ะ
Good afternoon, everybody. And thank you very much for the organization to invite me here to talk about subject of automotive and automotive PCB. HKPCA show, when I asked them, can you do two presentations? One is about the history of Thailand PCB industry, which I will talk on the day after tomorrow on Friday. So what else can you do? So I said, well, okay, more than half of the new PCB companies being constructed here in Thailand are targeting for automotive. So I thought maybe this is a good subject to talk about. It doesn't progress. In it?
Just a moment. Okay, I will connect to computer for you.
Okay.
2 minutes. You can talk
Okay.
something.
Yes.
Okay.
Okay.
2 minutes.
Okay. By the way, I came to Thailand the first time in 1986, and I visited KCE, which was only about 2-3 years old at the time. I met with Mr. Bancha Ongosit, and since then, many times I visited KCE. Of course, KCE is one of the largest automotive PCB makers in the world, and definitely number one in Thailand. Although the company seems to be expanding the horizon of applications gradually. And when it comes to automotive statistics, there are many available. And say, for example, as far as the number of cars is concerned, some company says 75 million cars are sold. Some companies say over 100 million cars are sold. And the only way you can really make sure is to go through company one by one and read the annual report, which can be almost 700 pages. So it takes a long time to have a final picture. But anyway, it doesn't move. Okay. This is compiled by International Organization of Motor Vehicle Manufacturers. And this is the number of cars made in 2023, about 94 million cars. This includes passenger cars, trucks, buses, all kinds of cars. And many consultant company says light vehicle, and the number is way low. But you can see about approximately 90 million cars are made. And definitely China is number one, about almost 30% of the cars made in China, followed by United States. And third is Japan. And all the way down. And you'll be surprised, like Korea, yes, but Spain, for example, It's not a very big country, but they produce quite a bit of cars. Seat, you see Seat just west of Barcelona. There's a big factory there. But when it comes to number of cars sold, it's different. This is okay. Oh, okay. So, China again, 30 million cars, same amount as they produced. The U.S., you remember, U.S. production was about 10 million. They sold 16 million. So they are importing about 6 million into the United States. And India took over number 3 now, over Japan. And Japan, remember, slightly over 8 million cars, sold only less than 5 million. There's a big problem for young people. If you're living in Tokyo, you have to pay, you have to show to buy a car proof of a parking. And parking in Tokyo, 1 month costs about 400,000. No, excuse me, $40,000. And then down payment, monthly payment, about the same amount. And then gasoline and license, and every 2 years you have to pay enormous amount of money. So it costs $10,000. So a young man, 25 years old, who is making maybe $25,000, $10,000 is a big money, big part of their, so they stop buying. And many of the cars sold in Japan are very small ones. They call the K, which means less than 1,000 cc. But interesting thing is 50% of the cars sold is all hybrid. Hybrid, yes. And you know, Toyota is number 1 in the world. Their sales of EV is very low because they make so much money on hybrid. They are saying, hey, maybe, and so they are concentrating on hybrid. And the European countries, in comparison to some of the big Asian countries, still buy a lot of cars. And I think that tells you the wealth of a country. If you are poor, you can't afford to buy a car. So Europe is still very rich, as you can see. Thailand, number 18. And this is going to change in the future. Okay? So, who was number 1? In 2023, Toyota, over 10 million car, followed by Volkswagen, Hyundai, Kia, Stellantis. Stellantis is the French, Peugeot, Renault, and then a Jeep, Chrysler, put together. And GM, Ford, Honda, Nissan. And interesting here, BYD and the Tesla, electric vehicle, now finally coming up, which shows you the future of the car trend. Another interesting thing, BMW. BMW sold 2.5 million cars. Sales value is $153 billion. And the $156 billion is GM. They have to sell little over 2 times more. So BMW, very expensive. Mercedes-Benz is also same way. Only 2.3 million and already very close to 2.5 billion. I have 2 Mercedeses. Actually, in the last 40 years, I keep buying Mercedes. But once I buy, I drive 20 years. No problem. And overall, instead of buying many cheap cars many times, one big reliable car is much economical. So here's the punch. Who are the top automotive PCB suppliers? 3 top companies are Japanese. Because sales of car in Japan is only 4.5 million, but 29 million cars are made by 8 Japanese companies. And that is the reason why they are supplying all these boards. And KC is right here, number 6. I have approximately 100 lists, but it's too long, so I cut it off. But with this, about $9 billion, maybe a little over $9 billion, maybe it could be $10 billion. Everybody wants this data to measure against competitors. Well, take a look at this average exchange rate. Particularly Japanese, they are about 110. And then all of a sudden, they changed 141. This morning, I saw it 156. So if we kept 2018-19 exchange rate, they are actually 50% more. These numbers would be 50% more. But unfortunately, for the sake of comparison, we have to use some common currency, and I had to use the US dollar. There's also a whole lot of different data about the world print circuit market. I shouldn't say market. This is a production, okay? Lot of consulting company, research company mix up the production and consumption. This, I'm talking about the production. Here, North America, South America, they are importing more than $500 million. But China is definitely number one, more than half, maybe 60%. And between China and Taiwan, they are almost 60, 70%. 2 biggest and powerful companies. Japan and the United States in year 2000 both had 32% share. Now it's down. China really killed it. So Thailand was a little over $3 billion last year. And Vietnam is right behind. But in the future, more and more investment is coming into Thailand than Vietnam. So I think that Thailand would just shoot up. Yes. EV sales is still growing, but the growth rate, like here you can see 40%, but now only about 20%. So it's slowing down. And China is still strong, but US way down, Europe way down. And there are several issues. One issue is there is not enough charging stations. But if you go to Shenzhen, there are more charging stations than gasoline stations. So it's a government policy. Number two, it's so inconvenient if you're renting a car. You have to go a long distance. You don't know where the hell this charging station is. And besides, electrical vehicle for equivalent size, it's a little bit more expensive. So common people struggling day to day, they cannot afford to buy. And the cruising distance also. I have, as I said, I have a 20 years old Mercedes. It's called R320, big station wagon. It's a diesel engine. And once I fill, it goes 650 miles, which is more than 1,000 kilometers. And I can go to Boston, back and Boston, no charge. If I use the electric, on the way somewhere I have to charge and spend about 2 hours waiting for a turn. It's so inconvenient. And proponent of EV says it's clean. It is clean, no gas coming out. But where the hell electricity is being produced? They are still burning gases, coals. And so overall, it's not that clean. So as I said, EV sales rate in 2024 is expected to be slower. And one of the reasons why Chinese are buying more EV is the price competition. They are cutting prices. The only two Chinese makers are profitable. All the rest of them, red ink. So you have to read the story behind what's happening. It's a repeat. So 2022, 37%, but then now we are coming down to about 20% growth. But it is still growing. A good American friend of mine recently had to change the battery of his Tesla Model S, 6 years old. Do you know how much he paid for new battery? $27,000. You can buy a small car. So this is the reality of EV. And I'm fairly positively sure Mr. Trump will be re-elected. And he hates EV. So situation in the US will change very drastically. So China certainly, this year still growing, as you can see. As a matter of fact, I have a data to June, but it was too late for me to change. This is a survey made in different countries. In the US, 67% of the people interviewed still like the gasoline engine. China, 33%. I think as of June, the total sales of a car, already more than 50% are EV in China. When I am not driving as a passenger, I like it. But when I have to drive, I have to always worry about charging. So this was the first quarter. BYD grew, but Tesla went down, the whole other went down. And the one thing, California still is more than 60% are Tesla, but in New York State, less than 50% are Tesla now. Tesla is losing its share. But I don't see any Chinese car because Mr. Biden put up 100% duty and it gets to be too expensive. So now BYD is making a plant in Mexico so that he can push out in the States. I inquired the dollar amount of PCBs used by Tesla Model 3. This was about several years ago. And the three PCB assembling makers, one Pegatron, and the another one is J-Bill. The another one I can't remember, a friend. He invested it for me, and they all came back with the answer, $400 PCB for Tesla Model 3 at that time. And I have been following this data for many years. So average usage of PCB by car is estimated to be about 100 from cheap end to the high end. And EV, and as low as $80 to about 200. Mercedes, BMW, Lexus, all these guys are using up to 200. And the EV is said to be about 200 to 300. And some EV may be using a little bit more PCB. And believing that 94 million cars manufactured in 2023, average usage of PCB per car is 100, then came out to be 9.4, which was the data I showed you before. It's not a coincidence, it is a fact. So, how do I see what kind of a PCB is used for automotive? SSB is a single-sided board, double-sided board, multi-layer board, typically between 4 and 10 layers. And the HDI boards, I found out, they are typically 4 layers up to about 18 layers for automotive. This heavy copper board, because EV requires a lot of power. And then high frequency boards, which is typically HDI, because if you are now driving, car has to be connected to the crowd, and to communication, you need a very high end of a PCB. And then flex rigid board. So these are the shares. And someone, my friend, asked me, Naka-san, can you make a forecast to 2025? I refused because I don't know what's happening tomorrow. But, all right, looking at the forecast of the car sales, I said, all right, oops, this may be it. But the interesting part, this is the IDC, International Data Corporation, predict the semiconductor usage of automotive. I have been tracing the relationship between semiconductor and the printed circuit board for the last 40 years. And whenever $1 of IC is used for product, 0.17 or 17 cents of a PCB is needed. So if you use the formula 88 billion semiconductor, multiply 17%, that's approximately $15 billion by 2027, 5 years from today. I think a lot of people agree this is the trend. So, navigation system, ADAS, automatic car. In a situation like this, you cannot see the lane. How the hell the car knows where to go? The only way you can safely drive a car like this is with internet. Okay, download the map. And that's where HDI, high-end of computation, is necessary. So at this moment, let me talk about PCB used by Tesla 3. They're all kind of boards by Nikkei Automotive, very, very useful magazine here. And this is the battery. They're all kind of batteries, but they have 1, 2, 3, 4 units. And you see the long flexible circuit board, which is connected to the battery cell. The lithium battery, if the temperature goes beyond 120 degrees, boom, explode. So it's very important to control the temperature. And then each one of the modules has a separate controller. So already 4 circuits, and the long flexible. So in this case, they use a cylindrical batteries made by Panasonic. And then this is surrounded with a copper heater cooler. And the lithium battery is interesting. If it goes too high, the temperature explodes. And once you catch a fire, you can never stop until it exhausts the energy. So that's one dangerous thing. But in the cold country, battery doesn't perform. So this is a cooling and heating. The heating is done by engine heater. Cooling has to have a separate thing. So it's a very, very complicated design here. And you can see the diagram. So this was a controller board enlarged. This is the onboard charger. You get 3-phase from outlet and capacitor here, and then get out the 2-phase DC to charge your battery. I think he has 1, 2, 3 different kind of boards. And this is inverter. You see, in the normal way, the normal outlet is about 170 in the US, 117 volts or 220 volts. Battery is typically 400. So if you take the juice and then onboard raises the AC to AC 400 and then AC to DC 400. And then 400 DC to 800 DC because the motor is 800. And then DC to AC. So many inverters and converters. That's where the power circuit is needed. Nikkei press people said, hey, this looks like an American flag, American continent. That's a joke. There are 17 silicon carbide for conversion. And now this is one of the hottest semiconductor devices today for automotive. This is autopilot plant, very famous. There are 2 chips designed by Tesla, but it is fabricated by Samsung in Korea. And this board, 14 layers, has 4,700 components mounted on here. Very, very, very complicated. And this is the actual board before components are mounted. AKM Meyway, Chinese company, which they bought from TTM Technology. There are few companies making this board. Olympic is another company. So, these are body control. The center body control, front line is the, oops, sorry. How do I go back? Okay, now I see. So this board has a function of MQ, microprocessor control, autonomous drive, and general electronic control unit, and cooling pump control, and power steering, headlamp, inverter, front drive, and multimedia radar system. And on this side, seat and doors, left side, seat go up and like that, moving, and the inverter, the pressure. So each 3 of them are different functions. You wouldn't realize because these boards are all buried under the dashboard. So you don't see anything, but actually they are there. And this is an 8-layer structure. One of the board, very interesting, is pin in, not the surface mounting, for some reason. So the card key entry, door open up automatically. 3-phase input, and the high voltage system. And there are 8 cameras in Tesla 3. And the triple forward camera, they don't use a LiDAR system for. And the display, radar, short radar, long range radar. So, all in all, at least 30 PCBs are used for Tesla. I think more like a 50, in my opinion. So it has been interesting to observe a flexible circuit board. NAK, Nippon Mectron, which has a big plant in here, Thailand, Ayutthaya. And now, several years ago, more than 60% of Nippon Mectron was FEC for Apple. Now they are down to about 40%, and the usage for automotive is increasing very, very strongly. Lamp. See, there is a lamp, and this is the gearbox. And there's a battery connection. Yeah. And gradually, the wire harness is being replaced with a flexible circuit board to weight control. And there's an interesting wiper. This wiper has a heater. So in a cold country in the morning when you turn on, wiper doesn't work. So heater will warm up and then start working. And there's a lot of ADAS. As you see, battery connection here. It's all flexible circuit. Hybrid. These are Prius, control board for Prius. There's another door control, PCB there. One big problem at this moment regarding automotive PCBs, a rapid price erosion in ordinary PCBs, particularly from Chinese PCB. As we saw in previous slide, 1/3 of the global car production made in China. And so everybody who wants to get into automotive, the only way they can win is to lower the price. So the once very profitable automotive circuit board business is getting to be not so profitable. So capable people going more and more into high end of a product like HDI, heavy copper, and whatnot. The Japanese makers dominated automotive production in Thailand with 100% share. But 1 year ago, BYD came, and then a lot of other companies coming. So eventually, I think a Japanese position will be eroded. I think this is probably end. But I think Thailand certainly in the future will become one of the largest country for producing PCBs for automotive industry. That's for sure, I'm convinced. Thank you very much.
ค่ะขอเสียงปรบมือให้กับดรฮายะนากาฮาระ NT Information ค่ะก็จบไปแล้วเนี่ยค่ะสำหรับหัวข้อการบรรยายในหัวข้อ Automotive Change and Development ค่ะซึ่งแน่นอนว่าสำหรับในหัวข้อต่อไปนะคะเราจะกลับมาเจอกันในช่วงเวลา 15:15 นาทีกับหัวข้อ The Influence of Future to Purify Converge AI Chipset on PCB Repeated Material ค่ะในช่วงนี้เดี๋ยวเราขออนุญาตพักเบรกด้านหน้าเวทีสักครู่และกลับมาเจอกันค่ะ